These are the answers to the AP Chemistry packet that covers topics 8.6 to 8.11. On this slide, you can see Unit 8 at a glance. Unit 8 is entitled Acids and Bases. In this video, we will take a look at topic 8.6, Molecular Structure of Acids and Bases, topic 8.7, pH and pKa, topic 8.8, Properties of Buffers, topic 8.9, Henderson-Hasselbalch equation, topic 8.10, Buffer Capacity, and topic 8.11, pH and Solubility. In the video description area, there is a link to the AP Chemistry course and exam description, which we call the CED for short, and there is also a link to the packet that accompanies this video. Topic 8.6, Molecular Structure of Acids and Bases. Here are some essential knowledge statements from the AP Chemistry course and exam description. The protons on a molecule that will participate in acid-base reactions and the relative strength of these protons can be inferred from the molecular structure. Strong acids such as HCl, HBr, HI, HClO4, H2SO4, and HNO3 have very weak conjugate bases that are stabilized by electronegativity, inductive effects, resonance, or some combination thereof. Strong bases, such as group 1 and group 2 hydroxides, have very weak conjugate acids. Carboxylic acids are one common class of weak acid. Common weak bases include nitrogenous bases, such as ammonia, as well as carboxylate ions. Electronegative elements tend to stabilize the conjugate base relative to the conjugate acid and so increase acid strength. Question 1. Hydrochloric acid ionizes in aqueous solution according to the equation shown above. So we see HCl plus H2O to produce the hydronium ion H3O plus and the chloride ion. This is a very strong acid, so you can see that the Ka is a rather large number, 1 times 10 to the 6. Now we are given the reaction where chloride reacts with water as a base to produce a molecule of HCl and the hydroxide ion. Part A, HCl and Cl- represent a conjugate acid-base pair. Calculate the value of Kb for the reaction represented by the equation above. Now, since HCl is a very strong acid, we would expect Cl- to be a very, very weak base. In fact, it's so weak, it is considered to be negligible or insignificant or unimportant. So that chloride ion does not affect the pH of the solution at all. In fact, any negative ion or anion that comes from a strong acid will be negligible and does not affect the pH of the solution. Let's go ahead and do that math. So looking at the equation sheet, we can see that the value of Kw is 1.0 times 10 to the negative 14, and we can also see that Kw is equal to the product of Ka times Kb for a conjugate acid-base pair. So that sets up an inverse relationship between Ka and Kb. In other words, if you have a very large Ka, like we do for this strong acid, then the Kb value will be very small for that negative ion. So when we do this math, it will be Kw, or 1 times 10 to the negative 14, divided by the Ka, 1 times 10 to the 6 for the hydrochloric acid. And when we do that math, we get a very small value of Kb for the chloride ion, 1 times 10 to the negative 20. Now, the answer to part B should be obvious from this very small magnitude of Kb for the chloride ion. Which of the following statements is true? Is the chloride ion not likely or very likely to react with water molecules to form hydroxide ions? And again, because of the magnitude of Kb for the chloride ion being very small, the answer is no, the chloride ion is not likely to react with water molecules to form hydroxide ions. So we consider the chloride ion to be neutral. So to justify your choice in part B, why is the chloride ion not very likely to react with water as a base to produce a molecule of HCl and the hydroxide ion? Remember that back in Unit 7 on equilibrium, topic 7.5, magnitude of the equilibrium constant, we learned that when K is very large, the reaction essentially proceeds to completion. But if K is very small, then the reaction barely proceeds at all from left to right. In fact, the reverse reaction goes essentially to completion. So the reverse reaction, where HCl reacts with hydroxide to produce chloride and water, that would be favored, not the forward reaction. So not only is chloride considered neutral, but these other four ions that come from these strong monoprotic acids, so HCl, HBr, HI, HClO4, and HNO3 are very strong monoprotic acids. So that makes these five anions, chloride, bromide, iodide, perchlorate, which is ClO4-, and nitrate, NO3-, these five anions, because they are produced in the ionization of a strong acid, are considered neutral. They are not bases at all. They have no effect on the pH of a solution. The reason why I have not included HSO4- is because that particular ion still has an H+ that it could lose. So HSO4- is actually a weak acid. So in general, these type of anions in the right side of this table are considered neutral. And as far as the cations on the left side of this table, these are also considered neutral. So when you have a cation from group 1 or group 2, such as sodium, potassium, calcium, and strontium, these are considered neutral and will not affect the pH of an aqueous solution. Now in question 2, I'm going to talk about carboxylic acids. Carboxylic acids are one common class of weak acid, and the general formula of a carboxylic acid is shown above, where the letter R refers to a group of atoms bonded to the CO2H portion of the molecule. The R group consists of atoms that are mostly carbon and hydrogen. Part A, acetic acid, CH3CO2H, is a weak acid found in household vinegar. It is one example of a carboxylic acid. Part 1, in the box at right, draw the Lewis diagram for acetic acid. So we know that there is a carbon doubly bonded to an oxygen, and that carbon is also singly bonded to an oxygen and then bonded to a hydrogen. But the R is CH3. So here is the Lewis diagram for acetic acid. You have a carbon bonded to 3 hydrogens, and that carbon is connected to the CO2H portion of the carboxylic acid molecule. The next part of this question, so part A, part 2, says write the balanced chemical equation for the ionization of acetic acid in aqueous solution. Here's the general formula for a weak acid, HA. Normally it reacts with water to produce the hydronium ion, H3O+, and its conjugate base, represented as A-. Let's go ahead and substitute for HA the acetic acid formula, which is CH3CO2H, and that hydrogen is going to be lost to water. So as it reacts with water to produce the hydronium ion, then CH3CO2- or acetate is the conjugate base. And as you have learned in my previous videos for Unit 8, the H3O+ or the hydronium ion is often used interchangeably with the H+ ion. So a more simplified, also acceptable view of this ionization reaction would be written like this reaction at the bottom of this slide. But the reaction that I'm showing in the box at the top of this slide, that is the preferred way to represent the ionization of a weak acid, where the weak acid molecule reacts with water to produce the hydronium ion and the conjugate base. Now let's take a look at part 3 of part A. It says the acidic behavior of a carboxylic acid, or RCO2H, is supported by the fact that its conjugate base, RCO2-, which is known as the carboxylate ion, is stabilized by resonance. Resonance helps to stabilize the conjugate base by delocalizing the negative charge over several atoms in the structure. Draw Lewis diagrams for the two resonance forms of the acetate ion, CH3CO2-. Now, you may recall that I first introduced the concept of resonance back in Unit 2. It was in topic 2.6, Resonance and Formal Charge, that I explained that when more than one equivalent Lewis structure can be constructed, resonance must be included as a refinement to the Lewis structure. So here on this slide, you can see two equivalent resonance structures of the ozone or O3 molecule. So the actual structure of ozone is considered to be an average or a hybrid of these two Lewis diagrams. There's a similar situation in the acetate ion. So when the H plus ion is removed from the acetic acid molecule, one Lewis diagram can be drawn on the left here, showing that we have a carbon-oxygen double bond as well as a carbon-oxygen single bond, but an alternate, equally equivalent Lewis diagram can be drawn where we switch the position of the single and double bonds. So the actual structure of the acetate ion is a hybrid or an average of these two Lewis diagrams. Again, resonance helps to stabilize the conjugate base or the acetate ion by delocalizing the negative charge over several atoms in the structure. Now, on to part B of this question. So at the top of this slide, we see the generic formula for a carboxylic acid, and that includes the CO2H portion. It's that H on the far right side of this generic structure. That is the acidic hydrogen atom. So that is the hydrogen atom that is lost as an H plus ion when the carboxylic acid molecule reacts as a proton donor. So for propanoic acid, CH3CH2CO2H, it's that hydrogen on the far right side of that structural formula. That is the hydrogen atom that is lost as H+. And there's a more complicated structural formula on the right side of the slide. This is salicylic acid. But let's focus on the CO2H portion of this carboxylic acid molecule, and that makes this hydrogen that I'm circling, that is the acidic hydrogen atom that is lost as an H+ ion. In question 3, it says that ammonia, NH3, is one example of a weak base. The ionization of ammonia in aqueous solution is represented by the equation shown above. So we can see in the equation that NH3 reacts with H2O to produce NH4+, which is the ammonium ion or the conjugate acid of ammonia, and the hydroxide ion. Ethylamine, CH3CH2NH2, is another example of a weak base that reacts with water in a similar way to ammonia. Write the balanced chemical equation for the ionization of ethylamine in aqueous solution. So ammonia and ethylamine, they both contain that nitrogen atom. These are examples of nitrogenous bases, and there's a lone pair of electrons on the nitrogen atom, and that is the place where it's going to be a proton acceptor. So water is behaving as an acid or a proton donor, and it's the nitrogen atom, that lone pair of electrons, that forms the new bond between the nitrogen and the hydrogen. And when the oxygen-hydrogen bond in water breaks, it forms the hydroxide ion. So the products of the reaction between ethylamine and water are the hydroxide ion and the ethyl ammonium cation. So that's going to be the product of this reaction. We have CH3CH2 NH3+, and then OH-. So there's our reactant, ethylamine, reacting with water to produce hydroxide and the ethyl ammonium ion. So notice that we have the correct charge on those ions on the right side of the equation. Now let's take a look at question 4. In question 4, we have 3 acids that are similar in their structure. They all contain a hydrogen bonded to an oxygen and then bonded to a member of the halogen family, whether it's chlorine, bromine, or iodine. The Ka of each acid is listed, and you also have the formula of the conjugate base, which is going to contain the halogen bonded to oxygen, and that carries a negative charge. So question 4 says the following. Information about 3 different acids is shown in the table above. Which of these acids is the strongest acid? Justify your answer in terms of the Ka value. In an earlier video, we discovered that when comparing different acids, the stronger acid is the acid that has the higher Ka value. So looking at these three acids, the highest Ka value would be for hypochlorous acid, or HOCl. And so just based on the process of comparing the magnitude of the Ka values for these three acids, we can say that HOCl is the strongest acid because it has the largest Ka value. But here in topic 8.6, molecular structure of acids and bases, we're looking for structural features that would make one acid different than another. And electronegative elements tend to stabilize the conjugate base relative to the conjugate acid, and so increase acid strength. Let's take a look at that. So here we have at the top of this slide a reaction between a water molecule and a general formula of HOX, where that's a hydrogen bonded to an oxygen and then bonded to X, where X represents either chlorine, bromine, or iodine. Now we know from periodic trends that chlorine is more electronegative than bromine, and bromine is more electronegative than iodine. So as we go from iodine to bromine to chlorine, the electronegativity of that atom increases. So how does that affect the strength of the acid? Well, there's two reasons why as the electronegativity of X increases, the strength of the acid increases. One reason is because as the electronegativity of X increases, electron density is drawn away from the HO bond. So you can see in this molecule I'm showing you at the bottom of the slide, as the X atom pulls electron density away from that HO bond, that causes the HO bond to become weaker and more polar. So you can see a partial positive charge on the hydrogen and a partial negative charge on the oxygen. And so that favors the breaking of the HO bond in the acid molecule. And that's what it is. If it's an acid, it's donating H+. So increasing the electronegativity of the X atom favors the formation of that particular process where that bond breaks. Now, another reason has to do with the stabilization of the conjugate base. So as the electronegativity of the X atom increases, then it stabilizes the conjugate base, the XO- ion, by pulling electron density away from the oxygen atom that carries the negative charge. Now, as the conjugate base becomes more stable, that favors, in this equilibrium, the formation of this XO- ion. And when you can favor the formation of the conjugate base, then that makes the strength of the acid increase. Now, moving on to question 5 in the packet, we can see, comparing these three acids in the table, that we're not talking about changing the electronegativity of an atom like chlorine or bromine or iodine. They all contain a hydrogen bonded to an oxygen bonded to a chlorine. But what changes in this table is the number of oxygen atoms that are present in these acid molecules. So question 5 says the following. Information about 3 different acids is shown in the table above. Which of these 3 acids is the strongest acid? Justify your answer in terms of the Ka value. So we start with 2.9 times 10 to the negative 8 for HOCl. Then when we add one more oxygen atom to that molecule, HClO2 has a Ka value of 1.1 times 10 to the negative 2, so it's getting larger. And then moving on to the HClO3 molecule, another oxygen atom is added to the structure, and now that Ka value is even larger. It's about 500. You already know that one of the 6 strong acids, if you've memorized them for the AP exam, includes HClO4. And if HClO4 is classified as a strong acid, then it's going to be a very large Ka value. So there's something going on here about increasing the number of oxygen atoms, and we'll talk about that. So the answer to this question, just based on the Ka, is that HClO3 is the strongest acid in this set because it has the largest Ka value. Let's take a look at the structural features that would explain why having additional oxygen atoms bonded to the central atom increases the acid's strength. So the acids shown in the table above are known as oxyacids. They contain a hydrogen atom bonded to an oxygen atom, and oxygen itself has a relatively high electronegativity. So it's not the central atom, the chlorine. That could be sulfur, that could be phosphorus, that could be nitrogen. It's about the number of oxygen atoms. So if oxygen has a relatively high electronegativity, then the presence of additional oxygen atoms bonded to the central atom increases the strength of the acid. And there are two reasons why this occurs. First, as the number of oxygen atoms increases, electron density is drawn toward these oxygen atoms away from the HO bond. And this causes the HO bond to become weaker and more polar, favoring the breaking of the HO bond in the acid molecule, so favoring the formation of H+. The second reason why this occurs is because of the stability of the conjugate base. So as the number of oxygen atoms increases, this helps to stabilize the conjugate base by allowing the negative charge to be delocalized or spread out over several oxygen atoms in the structure. Earlier in this video, when I was talking about the resonance forms for the acetate ion, that was an example of a carboxylic acid. So the carboxylate ion, or the conjugate base, is stabilized by having resonance to spread out or delocalize that negative charge over several atoms. Now here, at the top of this slide, you can see only one Lewis diagram that I've drawn for the ClO3- ion. But in fact, there are three different resonance forms or resonance structures that you could draw, and that just shows you that when you have additional oxygen atoms that are present in this oxyacid, then the conjugate base can be more stabilized by getting that negative charge to be delocalized or spread out over several oxygen atoms in the structure. And remember that as the conjugate base becomes more stable, this favors the equilibrium from left to right and therefore increasing the strength of the acid. So the more stable the conjugate base is, the stronger the acid is. Now there's one more feature that I want to mention, and this has to do with what's called polyprotic acids. In this example, we have sulfurous acid, which is a diprotic acid, H2SO3. I'm focusing on polyprotic acids here to show you that if you have more than one H+ ion that can be removed, you can see a structural feature that would explain why the first ionization event is easier than the second or possibly the third ionization event. So H2SO3 can lose two H+ ions. There's a Ka1 for the first ionization event, and there's a Ka2 for the second ionization event. If you had a triprotic acid such as H3PO4 or phosphoric acid, you could also have a Ka3. So sulfurous acid, H2SO3, is classified as a diprotic acid, and the stepwise dissociation of the acid is represented by the two equations shown above. Now the value of Ka1, which is the first ionization, is larger than the value of Ka2, which is the second ionization. So this can be explained because of Coulomb's law and electrostatic attractions. What you are removing is a positively charged H+ ion. And so it's easier to remove a positively charged H+ ion from a neutral molecule of H2SO3 than it is to remove an H+ or a positive H+ from a ion such as HSO3 that already carries a negative charge. So with a neutral molecule, it's easier to remove that positive H+ ion. With a negative ion, it's harder to pull that H+ ion from the negative ion. So if there were a third H+ to be removed, such as H3PO4, that would be even more difficult. Okay, now it's time for me to introduce our next topic in this packet. This is topic 8.7, pH and pKa. Here are some essential knowledge statements from the AP Chemistry course and exam description. The protonation state of an acid or base, that is, the relative concentrations of the weak acid, HA, and its conjugate base, A-, can be predicted by comparing the pH of a solution to the pKa of the acid in that solution. Now, when the solution pH is less than the pKa, then the acid form, HA, has a higher concentration than the base form, A-. On the other hand, when the solution pH is greater than the pKa, then the base form, A-, has a higher concentration than the acid form, HA. Acid-base indicators are substances that exhibit different properties, such as color, in their protonated versus deprotonated state, making that property respond to the pH of a solution. And to ensure accurate results in a titration experiment, acid-base indicators should be selected that have a pKa value that is close to the pH of the solution at the equivalence point. Question 6. The pKa values of two different acids are listed in the table above. Use this information to answer the following questions. So the first acid listed in the table is acetic acid, HC2H3O2. It has a pKa value of 4.74. And then the second acid listed in the table is the ammonium cation, NH4+. Its pKa value is 9.26. Part A. A solution is prepared by combining samples of acetic acid, HC2H3O2, and sodium hydroxide, NaOH. The pH of the combined solution is equal to 4.00. Which substance, the weak acid, acetic acid, HC2H3O2, or its conjugate base, acetate, C2H3O2-, is present in a higher concentration in the combined solution? Justify your answer. So in order to help you better understand the process of comparing pH and pKa, let's consider all three possibilities. If the pH is equal to the pKa, 4.74, then that would mean that the concentration of the weak acid is equal to the concentration of its conjugate base. If the pH is less than the pKa, then the concentration of the weak acid is greater than the concentration of its conjugate base. And if the pH is greater than the pKa, then the concentration of the conjugate base is greater than the concentration of the weak acid. So we know in part A, it says the pH of the combined solution is equal to 4.00. And since 4.00 is less than 4.74, then this situation that I'm highlighting on this slide is the correct answer. So which substance is present in a higher concentration in the combined solution? The answer is acetic acid, HC2H3O2, is present in a higher concentration because the pH of the solution is less than the pKa of the acid. Now, moving on to part B of this question, we're still talking about this comparison between HC2H3O2 and its conjugate base, C2H3O2-, but this time we have a particulate representation. So this is part B. A solution is made by combining samples of acetic acid and sodium acetate. A particulate representation of a small portion of this solution is shown below. Water molecules and sodium ions are not shown. Is the pH of the solution represented in the diagram less than, greater than, or equal to 4.74? Justify your answer. So when we count the particles in this diagram, we can see 4 molecules of the weak acid, acetic acid, HC2H3O2, and then we can see 8 ions of acetate, which is the conjugate base. So since the concentration of the acetate is greater than the concentration of acetic acid, that means that there's more of the conjugate base than the weak acid. So the pH must be greater than 4.74 because the concentration of the conjugate base is greater than the concentration of the weak acid. So in parts A and B of question 6, we were comparing the concentration of acetic acid with the concentration of acetate. That's the conjugate acid-base pair. So now in part C, our conjugate acid-base pair is going to be ammonium, which is NH4+, and ammonia, which is NH3. So here in part C, we have an acid-base titration. You can see that we're starting with a weak acid because the pH begins at somewhere between a pH of 4 and 5. It says that in part C, a student titrates 50.0 milliliters of 1.0 molar ammonium chloride with a solution of 1.0 molar sodium hydroxide. So here we have an example of a weak acid being titrated with a strong base. At the very beginning of the titration, before any of the titrant or the sodium hydroxide is added, there should be mostly ammonium ions present in solution. And then at the equivalence point in the titration, we can assume that essentially all of the ammonium ions have been converted into its conjugate base, which is ammonia or NH3. But it's that middle portion of this titration curve between the beginning and the equivalence point that are labeled as points X, Y, and Z that we have to decide, is there a higher concentration of NH4+, or is there a higher concentration of NH3? In my earlier video where I talked about acid-base titrations, you remember that there's something special that happens at the half equivalence point in an acid-base titration. At the half equivalence point in an acid-base titration, the concentration of the weak acid is equal to the concentration of its conjugate base. So at point Y, which is the half equivalence point, the concentration of NH4+ ammonium should be equal to the concentration of NH3 ammonia. So I'm going to go ahead and circle that. So in part C, for point Y, there should be an equal concentration of the conjugate acid and the conjugate base at the half equivalence point. But now we have to focus on points X and Z and decide which one of those substances is present in a higher concentration. So when you're comparing pH with pKa, if the pH is less than the pKa, there should be a higher concentration of the acid. So looking at point X on this curve, since the pH is slightly less than the pKa, which is at the half equivalence point, there should be a greater concentration of the acid, NH4+, as compared to the conjugate base, NH3. So I'll go ahead and circle that. So if NH4+ is present in a higher amount, that's because the pH is less than the pKa. And now you can already anticipate what's going to happen for point Z. So now at point Z in the titration curve, since the pH is greater than the pKa, then there should be a higher concentration of the conjugate base as compared to the conjugate acid. So now at point Z, the concentration of the base, ammonia, should be greater than the concentration of its conjugate acid, NH4+. All right, so that is the answer to part C. And now, before we move on to question 7, I want to talk a little bit about acid-base indicators. So acid-base indicators have this very important and useful property in that they can display at least 2 different colors depending on the pH of the solution. So there are 2 common examples of laboratory situations where you would use an acid-base indicator. One example is that you're trying to get an approximate measurement of the pH of a solution. So you add a few drops of an acid-base indicator to the solution, and depending on the color that you observe, this will give you a rough or approximate measurement of the pH of that solution. Another very important application of an acid-base indicator is using it during an acid-base titration. As you already know, that during an acid-base titration, there is the equivalence point. So when the equivalence point is reached, one reactant has reacted completely with the other reactant according to the stoichiometry of the chemical equation. And when you are very close or at the equivalence point, there's often a rapid change in pH. So if you choose the appropriate indicator, then you can get the indicator to change color very near or exactly at the equivalence point. So when the indicator changes color, this is a signal to stop the titration. We call that the end point. That when an observation, usually a color change, occurs, this is the signal that you have arrived at the equivalence point. So you'll notice that in this table, we have 3 examples. There's plenty of acid-base indicators out there. I'm just showing you 3 examples, and they are methyl red, which could be either red or yellow, depending on the pH. We have bromothymol blue, which could be either yellow or blue, depending on the pH. And then we have phenolphthalein, which could be either colorless or pink, depending on the pH of the solution. So what you also notice in the table is the pKa value. And the reason why there is a pKa value is because, and I find this very interesting, is that while acid-base indicators can be used in acid-base titrations, the indicator itself is an example of a weak acid. And that's why there is a pKa value listed for each indicator. So, as you can see on this slide, it says that an acid-base indicator is a substance that can exist in 2 different forms, each with a different color. The acid form of the indicator is represented as HIN, where the letter H represents the hydrogen atom that is lost as H+, and then IN simply refers to the rest of the chemical formula or the rest of the molecule. So when HIN loses H+, it forms the conjugate base, and so the conjugate base form of the indicator is represented as IN-. So here on this slide, you can see that when the HIN molecule in its acid form reacts with water, it produces the hydronium ion H3O+, and it also forms the conjugate base represented as IN-. Now let's go ahead and take a look at a specific example. I'll start with methyl red. So methyl red has a pKa value of 5.1. So what happens is that when the pH of the solution is approximately 4 or lower, then the red form or the acid form of the indicator dominates in solution. But when the pH of the solution is approximately 6 or higher, then the conjugate base form or the yellow form of the indicator dominates. So now pH versus pKa, let's take a look. If the pH of the solution is less than the pKa of the indicator, the acid form, HIN, has a higher concentration than the conjugate base form, IN-. I'm going to use sort of a Le Chatelier's principle argument to explain which side of this equilibrium system would be favored. So if the pH of the solution is less than the pKa, then there should be an excess amount of the hydronium ion in solution, and that would favor the formation of the reactants. That's why the solution would appear red if you have a pH below 4. So an excess amount of hydronium would drive the equilibrium toward the reactants, toward the left. Now, on the other hand, if the pH of the solution is greater than the pKa of the indicator, now the conjugate base form, or IN-, would have a higher concentration than the acid form, HIN. Again, I'll try to use a Le Chatelier's principle argument. So if the pH is greater than the pKa, now we have an excess amount of the hydroxide ion, and that is going to drive the equilibrium from left to right. So with an excess amount of hydroxide, or not enough hydronium, the hydroxide ions would react with the HIN molecules, favoring the formation of the IN-, or the conjugate base form. So if the pH is higher than 6, then you would expect a yellow color for methyl red. But you might be wondering, what happens if the pH is between 4 and 6? That would be sort of the transition region. So when the pH is in between 4 and 6, like approximately pH 5, if the pH is roughly equal to the pKa, then there would be an approximately equal amount of both the acid form and the conjugate base form. So most likely the solution at that pH, which is kind of in the middle, would be approximately, well, somewhere between red and yellow, so probably orange. So there's always going to be that transition for an indicator where it changes from one form to the other, and then that color change would occur. All right, now let's go ahead and take a look at question 7, which is specifically talking about bromothymol blue. 3 solutions of bromothymol blue, which has a pKa of 7.0, were prepared. with different pH values as shown in the table below. Write the expected color for each solution. So if the pH is 4, then it should be yellow because it says in the table that the pKa is 7, and so it should be yellow below pH 6, in which the acid form of the indicator dominates. And if the pH is 10, well, it says in the table that the color of bromothiamyl blue should be blue above pH 8, so now the pH is greater than the pKa and the conjugate base form dominates. Hopefully you can imagine what would happen if the pH was 7. If the pH were 7, then now we have a roughly equal amount of both the acid form and the conjugate base form, and you would see that combination of yellow and blue, which is green. And here's a picture of what that looks like in the laboratory. So on the left, we have a yellow solution, which is going to have a pH less than the pKa. On the right, we have a blue solution in which the pH is greater than the pKa. And in the middle, we have a green solution in which the pH is approximately equal to the pKa. So before I talk about question 8 in this packet, let me give you some advice about choosing the best indicator to use for an acid-base titration. And this advice is highlighted at the top of this slide. So when selecting an acid-base indicator for a titration, it is important to choose an indicator that will change color at or very near the equivalence point. Therefore, the best indicator to choose is the one with a pKa value that is close to the pH of the solution at the equivalence point. All right, this is question 8 in your packet. It says the structural formula of sorbic acid, HC6H7O2, is shown above. Potassium sorbate, which has the formula KC6H7O2, is commonly added to diet soft drinks as a preservative. A student is given a stock solution of potassium sorbate of unknown concentration. The student titrates a sample of the stock solution with hydrochloric acid, HCl, using both an indicator and a pH meter. Now, so that there is no confusion about the difference between sorbic acid and potassium sorbate, take a look. At the top of the slide, you can see the chemical formula for sorbic acid, HC6H7O2. By the way, earlier in this video, I talked about the formula of a carboxylic acid. This is an example of a carboxylic acid. On the right side of this formula, you can see that familiar CO2H group, which is featured in carboxylic acids. The H on the far right of this molecule is the one that is lost as an H plus ion. So when that H plus ion is removed, it forms what is called the sorbate ion, and this carries a -1 charge. The formula of the sorbate ion, which is the conjugate base of sorbic acid, is C6H7O2-. So therefore, the formula potassium sorbate would simply be a potassium ion and the negative C6H7O2- ion together as an ionic compound or dissolved in aqueous solution. So we have a titration experiment in which the student titrates a sample of potassium sorbate with hydrochloric acid. So it's going to be a reaction between a weak base and a strong acid. So when you write the net ionic equation for a reaction that takes place in aqueous solution, it's important to consider the properties of each substance. And you might ask yourself the following question about each substance in the chemical equation. Do I split up the chemical formula into separate ions, or do I leave it unchanged exactly as written? Here are some guidelines for making that choice. If you have an aqueous ionic compound, such as sodium chloride, or any aqueous ionic compound that contains one of the 4 soluble snap ions, so the snap ions are sodium, nitrate, ammonium, or potassium, or if you see one of the 6 strong acids in aqueous solution, such as hydrochloric acid or hydrobromic acid, then you would split up that chemical formula into separate positive and negative ions. But on the other hand, if you see something that is labeled as a pure gas, a pure liquid, or a pure solid, or if you see a substance that you know is covalent or molecular, a substance that normally exists in the form of molecules, such as H2O, or you see a molecular version of a weak acid, such as HF, hydrofluoric acid, or the molecular version of a weak base, such as ammonia, NH3, then you would leave that chemical formula unchanged, exactly as written. So our first reactant in part A is potassium sorbate. Hopefully you can tell that potassium sorbate in aqueous solution consists of potassium ions and sorbate ions. So that is an aqueous ionic compound. Potassium is one of those soluble snap ions, so you would split up potassium sorbate into separate potassium ions and sorbate ions. The next reactant is hydrochloric acid, which is on your list of 6 strong acids. So in aqueous solution, you can split up hydrochloric acid into H plus and Cl minus. Now for the products, which we are not given in this chemical equation, we have to come up with them on our own, we know that an acid-base reaction is taking place. So when you have an acid-base reaction, there's always going to be proton transfer, the transfer of an H plus ion from the acid to the base. So the H plus combines with the C6H7O2 minus to produce a molecule of sorbic acid. So because sorbic acid is not a strong acid, it's a weak acid, that means it's only partially ionized in aqueous solution. So we're going to write the chemical formula of sorbic acid exactly as it's written. We're not going to split it up into separate ions. It is a weak acid. And then the other product of this chemical reaction is potassium chloride. But just like potassium sorbate, potassium, which is a soluble snap ion, potassium chloride is soluble and should be split up. It's a soluble ionic compound, so potassium chloride is written as separate potassium ions and chloride ions. Now that we've finished analyzing the properties of each substance, the reactants and the products, we can cross off any spectator ions that appear on both sides of the equation. So we can cross off the potassium ion on both the left and the right, and we can cross off the chloride ion on both the left and the right. Now what remains is the net ionic equation. So in this reaction between a weak base and a strong acid, the sorbate ion, which is a weak base, reacted with H plus from the strong acid to produce the weak acid, sorbic acid. Another way that you might have written this net ionic equation is to substitute hydronium for H plus. But remember that hydronium is H3O plus. So to balance this equation, you'd also have to show water on the right side of the equation as a product, because water is the conjugate base of the hydronium ion. So whether you show the net ionic equation like this, the sorbate ion plus H plus to produce a molecule of sorbic acid, or whether you show the sorbate ion reacting with the hydronium ion to produce sorbic acid and a molecule of water, either one of those possible answers would be correct. Now let's move on to part B of this question. Here we are looking at the titration curve for this experiment in which a solution of potassium sorbate is titrated with a solution of 1.25 molar hydrochloric acid. And looking at the shape of this titration curve, we can see that there's that rapid decrease in pH that occurs at 30 milliliters, after 30 milliliters of the titrant has been added. So that is the location of the equivalence point in this experiment based on that decrease in pH and the general shape of the curve. So in part B, it says the student titrated a 50.0 milliliter sample of potassium sorbate with 1.25 molar hydrochloric acid. The titration curve is shown above. Use the information from the titration curve to answer the following questions. So in part 1 of this question, it says to calculate the value of the concentration of the sorbate ion in the stock solution. Let's start with the volume of the titrant, 30 milliliters, that was required to reach the equivalence point. And then we also know the concentration of the titrant, which is 1.25 moles per liter for the hydrochloric acid. Remember that volume in liters times the concentration in units of moles per liter will give you the moles. So the volume in liters would be not 30, but rather divide by 1,000. So 30 divided by 1,000 would be 0.03 liters. Again, the molarity of the hydrochloric acid is 1.25 moles per liter. And if we did this calculation, this would tell us the number of moles of hydrochloric acid that was required to reach the equivalence point in this titration. Now, from the stoichiometry of the equation that we wrote in part A, we can see that there's 1 mole of the sorbate ion reacting with 1 mole of H+. So what does that mean in terms of the stoichiometry and the mole ratio? It means that there is 1 mole of sorbate consumed for every 1 mole of HCl in this acid-base reaction. So now if we do this calculation of 0.03 liters times 1.25 moles per liter, and again, based on that 1-to-1 mole ratio in the stoichiometry, we discover that 0.0375 moles of sorbate was present in the stock solution. This number is not our final answer because we're looking for concentration that would be moles per liter. So what we need to do now is look at the volume of the potassium sorbate stock solution that was titrated in this experiment. Remember, it's moles divided by liters. So 50.0 milliliters becomes 0.05 liters when you divide by 1,000. So 0.0375 moles of the sorbate ion divided by the volume, 0.05 liters, and we get our answer. So the answer to part B number 1 is 0.75 moles per liter. Now, before I move on to part B number 2, I'll just remind you of something I had presented in the earlier video on titration calculations, where if you have a 1-to-1 mole ratio between the acid and the base, you can use the following equation, and that is molarity of the acid times volume of the acid equals molarity of the base times volume of the base. But again, that equation only works if you have a 1-to-1 mole ratio between the acid and the base. And we do in this example. There's 1 mole of sorbate for every 1 mole of HCl. So the molarity of the acid is 1.25 moles per liter. The volume of the acid, the titrant that was used to reach the equivalence point, is 30 milliliters. The molarity of the base is what we are trying to find. And the volume of the base is that 50.0 milliliter sample of that potassium sorbate stock solution that was given in this question. So you might wonder about the units for volume, that normally the volume is in liters, but as long as you have the same unit of volume on both sides of this equation, the proportion is still true. So I can use 30 milliliters and 50 milliliters and still get the same answer. I don't have to use my units in liters. So if I solve for the molarity of the base, it would be 1.25 times 30 divided by 50. And when I do that math, I get the same answer that I mentioned earlier, which is that the concentration of the sorbate ion in the stock solution is 0.75 moles per liter. All right, now let's take a look at part B, number 2. So earlier in the video, I was talking about choosing an indicator, and the advice that I had given you is the following. When selecting an acid-base indicator for a titration, it is important to choose an indicator that will change color at or very near the equivalence point. Therefore, the best indicator to choose is the one with a pKa value that is close to the pH of the solution at the equivalence point. So you can see that the equivalence point is at 30 milliliters, and that puts the pH of the solution somewhere between 2 and 3. And looking at our 4 choices, which of the indicators listed at right would be the best choice for determining the endpoint of the titration? We have a pKa of 2.0, 5.1, 7.0, and 9.3, but we're going to choose thymol blue. That would be the best choice for determining the endpoint of the titration because its pKa value of 2.0 is very close to the pH of approximately 2.5 of the solution at the equivalence point. Now let's move on to part B, number 3. It says, estimate the value of pKa for sorbic acid. So we've already established that the equivalence point occurs at 30 milliliters and the half equivalence point occurs at 15 milliliters. So you might be a little confused about, does it make a difference whether we are titrating a weak acid with a strong base or whether we're titrating a weak base with a strong acid? Can we still get the same information about pH equals pKa? Well, here in an earlier video, I had presented this curve, and this is an example of a weak acid being titrated with a strong base, and I said that at the half equivalence point, the pH equals the pKa of the weak acid. I also presented this curve in an earlier video, and this is the titration of a weak base with a strong acid. So technically, you could say it two different ways. You could say the pOH is equal to the pKb of the weak base, but you also can say that the pH is equal to the pKa for the weak acid. Now, the conjugate acid could be something like ammonium or Hb+, but in this case, we do have a conjugate acid-base pair. We have sorbic acid and the sorbate ion. So at this half equivalence point, those two concentrations are equal. And in this question, part B, number 3, it's not talking about the Kb or the pKb for the sorbate ion. It's talking about the pKa for sorbic acid. So we can go ahead and use that same relationship, that at the half equivalence point, the pH equals the pKa, referring to the weak acid in this conjugate acid-base pair. So looking at the graph, looks like the pH of the solution after 15 milliliters of the titrant has been added is just under 5. So I would say, estimating it, it's approximately 4.8 or 4.9. So at the half equivalence point, the concentration of sorbic acid is equal to the concentration of its conjugate base. All right, now let us move on to part C of this question. It says the pH of a soft drink is 3.37 after the addition of a sample of potassium sorbate. Which substance, the sorbic acid or the sorbate ion, has a higher concentration in the soft drink? Justify your answer. So in order to answer part C correctly, you need to remember this highlighted essential knowledge statement from topic 8.7, pH and pKa. And that is that when the pH of the solution is less than the pKa, then the acid form, or HA, has a higher concentration than the base form, or A-. So the correct answer to question C is the following. A pH of 3.37 is less than the pKa of sorbic acid, which we already estimated from the graph to be approximately 4.8 or 4.9. So since the pH is less than the pKa, the concentration of sorbic acid is greater in the solution than the concentration of the conjugate base. Now let's take a look at our next topic in the packet. This is topic 8.8, properties of buffers. Here is an essential knowledge statement from the AP Chemistry course and exam description. A buffer solution contains a large concentration of both members in a conjugate acid-base pair. The conjugate acid reacts with added base, and the conjugate base reacts with added acid. These reactions are responsible for the ability of a buffer to stabilize pH. So before we take a look at question 9 in the packet, I'm going to spend some time teaching you about the properties of buffers and how they work. So here on this table, you can see several examples of weak acids and their corresponding conjugate bases. So we can use conjugate acid-base pairs to create a buffer as long as the acid and the base are generally weak. So what are the components of a buffer solution? A buffer solution contains approximately the same number of moles or equimolar amounts of a conjugate acid-base pair. So you could either use a weak acid and its conjugate base, or you could use a weak base and its conjugate acid. So for example, let's say you picked the first acid listed in this table, which is chlorous acid, HClO2. If you combine in solution the HClO2 with its conjugate base, which would be the chlorite ion Cl2-, then the pH of that buffer solution should be around 1.96. Remember that pH equals pKa when the concentration of that conjugate acid-base pair is present in equimolar amounts. So using the information from this table, there are lots of buffer solutions that could be prepared. For example, if we had an equimolar amount of HF, hydrofluoric acid, and the fluoride ion, which is its conjugate base, then the pH of that buffer solution would be 3.17, which is equal to the pKa for hydrofluoric acid. If instead you use a mixture of equimolar amounts of acetic acid and acetate, then the pH of that buffer solution would be 4.74, which is equal to the pKa for acetic acid. if you have a mixture of H2PO4-, which is called dihydrogen phosphate, and HPO4-2-, which is called hydrogen phosphate, then if you have an equimolar mixture of these two ions, the pH of that buffer solution would be 7.20, which is the pKa for the dihydrogen phosphate ion. If you have a mixture of ammonia, which is a weak base, and ammonium, NH4+, which is the conjugate acid, then if you have an equimolar mixture of NH4+ and NH3, the pH would equal 9.26, which is equal to the pKa of the ammonium ion. What is the approximate pH of a buffer solution? Consider the equilibrium constant expression for a weak acid. If a buffer solution is prepared that contains equimolar amounts of a weak acid and its conjugate base, so if HA and A- have the same concentration, or if the weak base B has the same concentration as its conjugate acid, Hb+, then those terms would cancel out in the equilibrium constant expression, and the Ka would be equal to the concentration of the hydronium ion, and the pH is equal to the pKa. Therefore, the pH of a buffer solution should be similar to the pKa of the weak acid that was used to create the buffer. What are the properties of a buffer solution? A buffer solution can maintain the pH at a fairly constant level when either a strong acid or a strong base is added to the solution. So when a small amount of a strong acid is added to the buffer solution, the pH will decrease slightly. So here is the Ka expression. Suppose you start with a buffer solution in which the concentration of HA, the weak acid, is the same as the concentration of the conjugate base, A-. And if a small amount of a strong acid is added to the buffer, then this chemical reaction would take place. A- would react with the hydronium ion from the strong acid to produce the weak acid HA and water. Look at the Ka expression. The concentration of A- would decrease. The concentration of HA would increase. And here are some examples. Now the numbers are no longer equal, but 0.95 and 1.05, or 0.9 and 1.1, or 0.85 and 1.15. But the important point is that as long as the ratio of the conjugate base to the weak acid remains fairly constant, then the pH of the buffer solution will not change very much. Now take a look at what happens if we add a small amount of a strong base to the buffer solution. The pH will increase, but only slightly. So for example, if a small amount of a strong base is added to this buffer, then the molecules of HA react with the hydroxide ions from the strong base to produce the conjugate base A- and water. So in the Ka expression, concentration of A- would increase, concentration of the weak acid HA would decrease, and you might have numbers such as 1.05 over 0.95, or 1.1 over 0.9, or 1.15 over 0.85. But again, the important point is that whether a small amount of a strong acid or a strong base is added to the buffer, as long as the ratio of the weak base to its conjugate acid in that partnership remains fairly constant, then the pH of the buffer solution will not change very much. I would also like to mention that this concept of how a buffer solution works is very closely related to certain types of acid-base titrations. So on the left, you see a titration curve for a weak acid titrated with a strong base, and on the right, you see an example of a titration curve where a weak base is being titrated with a strong acid. The part that I'm highlighting on these two titration curves is that middle region. The reaction mixture in the titration behaves as a buffer solution in this region because the concentration of the weak acid and its conjugate base are approximately equal during this part of the titration. So that portion of the titration curve is sometimes referred to as the buffer region or the buffer zone. Now, if you look on this slide, you can see I have a beaker and it contains a buffer solution. So what's in this beaker? Well, if you look at the particle diagram, you can see that there are 4 particles of the weak acid, HA, and there are 4 particles of the ion, A-. So this is a buffer solution that contains equimolar or equal mole amounts of acetic acid, which has the chemical formula HC2H3O2, so that's a weak acid, but it also has the same number of moles of the acetate ion, which is the conjugate base, and that has the chemical formula C2H3O2-. So equimolar amounts of acetic acid and acetate in this buffer, and the pH is equal to the pKa for acetic acid, and that's 4.74. Now, here comes the change. A small amount of a strong acid is added to this buffer solution. So the chemical reaction that will take place is between the hydronium ions of that strong acid and the acetate ions that are present in that buffer. And when that chemical reaction takes place, the products of that reaction are acetic acid and water. So as a result, the concentration of the acetate ion in the buffer will decrease a little bit, and the concentration of acetic acid in that buffer will increase a little bit. Now, count the particles in the new beaker that's on the right side of this slide. Instead of 4 molecules of acetic acid and 4 ions of acetate, you can see now 1, 2, 3, 4, 5 molecules of acetic acid and 3 ions of acetate. So do we still have a buffer solution? Yes, but now in that buffer solution, the concentration of acetic acid is no longer equal to the concentration of acetate. So because a small amount of a strong acid is added, now the concentration of acetic acid is slightly greater than the concentration of acetate. So it's still a buffer solution, but the concentration of each of those buffer components has changed a little bit. Did the pH go down? Yes, but only by a small amount. So that did behave as a buffer. The pH did change, but only by a small amount. So a good buffer will keep the pH relatively constant. Now let's go ahead and talk about what would happen if, instead of adding a small amount of a strong acid, let's go ahead and add a small amount of a strong base. So we start over with that buffer solution that contains an equimolar amount of acetic acid and acetate. So the chemical reaction that will take place now is between the hydroxide ions of that strong base and acetic acid. So as a result of that chemical reaction between acetic acid and the hydroxide ions, it produces acetate and water. So when a small amount of a strong base is added, the concentration of acetic acid will decrease a little bit, and the concentration of the acetate ion will increase a little bit. Let's count the particles in the beaker on the right side of this slide. So now instead of 4 molecules of acetic acid and 4 ions of acetate, we can see in that beaker on the right, now there's only 3 molecules of acetic acid and there are 5 ions of acetate. Do we still have a buffer solution? Yes, but now in this solution, the concentration of acetic acid and acetate are no longer equal. The concentration of acetate is slightly greater than the concentration of acetic acid. Did the pH go up? Yes, but only a little bit. So the pH increases, but only by a small amount. So a good buffer will keep the pH relatively constant when either a small amount of a strong acid is added to the buffer or when a small amount of a strong base is added to the buffer. So what happens when a strong acid is added to a buffer solution is the following. A strong acid is added, the conjugate base in the conjugate acid-base pair reacts with the hydronium ion from the strong acid to produce more of the weak acid. So the value for the concentration of the conjugate base decreases, the value for the concentration of the weak acid increases, and the pH will decrease, but only slightly. What happens when a strong base is added to a buffer solution? After you add the strong base, the weak acid will react with the hydroxide ions from the strong base to produce the conjugate base and water. So the value for the concentration of the weak acid will decrease, the value for the concentration of the conjugate base increases, and the pH will increase, but only slightly. All right, now we come to question 9 in the packet. Question 9 says the following. A buffer solution is prepared by combining 500.0 milliliters of 2.00 molar acetic acid with 500.0 milliliters of 2.00 molar sodium acetate. And the Ka for acetic acid is 1.8 times 10 to the negative 5. So we know that volume times molarity equals moles. And for these two solutions that are being combined, we have the same volume and the same concentration. So therefore, we have the same number of moles of acetic acid as we have number of moles of acetate. So for this buffer solution, there are equimolar amounts of acetic acid and the acetate ion. Therefore, the pH equals the pKa for acetic acid. Now, the pKa is the negative log of the Ka. So the pH of this solution is equal to the negative log of 1.8 times 10 to the negative 5. And that's 4.74. So that is our answer to part A. And now moving on to part B, we have to write the net ionic equation for the reaction that occurs when nitric acid, HNO3, or any strong acid is added to this buffer solution. There are two components in the buffer solution. There's acetic acid, the weak acid, and there's acetate, the conjugate base. Since we're adding a strong acid to this buffer, then we need an acid-base reaction to occur. So it's going to be the weak base, the acetate ion, reacting with either H plus or the hydronium ion, which comes from the strong acid. So when the acetate reacts with the hydronium ion, it would produce acetic acid as well as water. And now we can use the equation that we wrote in part B to answer part C. It says when a small amount of nitric acid or any strong acid is added to this buffer solution, the concentration of acetic acid will, and the answer is increase. You can see that acetic acid is being produced as a product in the equation that we wrote in part B. And the concentration of the acetate ion will decrease. Again, you can see it's being consumed as a reactant in the equation that we wrote in part B. So now, moving on to part D, we're going to do some calculations using a rice table. In part D, it says, suppose that 4.0 milliliters of 10.0 molar nitric acid is added to 1 liter of this buffer solution. Calculate the pH of the buffer solution after the nitric acid is added to it. A rice table is shown below to guide you. If you're wondering where that reaction came from in the rice table, this is the reaction that was written, or the equation that was written in part B. So when a strong acid is added to a buffer, it's going to be the weak base, in this case the acetate ion, that reacts with the strong acid in the form of these hydronium ions, and it will produce additional amount of the weak acid. So we have acetate reacting with hydronium to produce acetic acid and water. And if you're wondering, where did the 1.00 mole come from for the acetate ion and the acetic acid, it goes back to the instructions that were given for how this buffer was prepared. So 500 milliliters of 2 molar acetic acid was combined with 500 milliliters of 2 molar sodium acetate. Remember that volume times molarity equals moles. So 500 milliliters is 0.5 liters times 2 mole per liter, and 0.5 times 2 is 1. So if you're wondering, where did that 1.00 mole came from? It came from the instructions for preparing the buffer. Now let's take a look at the amount of moles of the hydronium ion. So 4.0 milliliters, when you divide by 1,000, that would be 0.004 liters. And it's a 10 molar solution of nitric acid. So 0.004 liters times 10 moles per liter, that gives us 0.004 times 10 is 0.04. That's the number of moles of nitric acid that was added to the buffer solution. So that number goes right here in the rice table for the number of moles of the hydronium ion. Now let's process the rest of this rice table. Since the amount of moles of the hydronium ion is the limiting reactant in this experiment. Let's go ahead and have that be the change in our change row of the rice table. So the number of moles of acetate will decrease by 0.04. The number of moles of the hydronium ion will be consumed. That will decrease by 0.04. And then we're producing acetic acid. So the number of moles of acetic acid will increase by 0.04. 1 minus 0.04 is equal to 0.96. Obviously, we've decreased our concentration of hydronium to a very small number, so it's essentially 0. And then 1 plus 0.04 is 1.04. Now, we have 1 liter of the buffer, and if we add 4 milliliters, technically the volume of the solution is now 1,004 milliliters, but we are given instructions to assume, for the purpose of making the math simple, that the final volume of the solution remains constant at 1.00 liters. So if I have the number of moles in the rice table, then divided by 1, it's going to be the same number for the concentration. So my concentration of acetate is 0.96 molar, and my concentration of acetic acid is 1.04 molar. What do I do now to get the pH? I will simply plug in the numbers for the concentration of acetate and acetic acid into the Ka expression, and I will solve for the concentration of the hydronium ion, and then take the negative log to get the pH. So if I do the math of 1.8 times 10 to the negative 5 times 1.04 divided by 0.96, the concentration of the hydronium ion is equal to 2.0 times 10 to the negative 5. Now, you can already remember from earlier in the video that when we add a small amount of a strong acid to a buffer, the pH should decrease, but only by a small amount. The original pH of the buffer was 4.74. When you take the negative log of the concentration of hydronium, we get the negative log of 2 times 10 to the negative 5 is 4.70. So we can see that the pH did decrease, but only by a very small amount. And the reason why the change in pH was a very small magnitude is because of this ratio that I had mentioned earlier in the video. I'll go ahead and highlight that on this slide. So take a look in the Ka expression. If you can keep the ratio of the weak base to the weak acid fairly constant and not changing very much, then your pH will change, but only by a small amount. So before the strong acid was added, the ratio of acetate to acetic acid was exactly 1. Now, after the strong acid was added, the ratio is 0.96 divided by 1.04. So did the ratio change? Yes, but only by a small amount, and that's why the pH only changed by a small amount. Now, in part E, let's consider what would happen if we added this same amount of strong acid to pure water. And what you should see in part E is that now when there is no buffer, the pH will change by a very large amount. So we have 4.0 milliliters of 10 molar nitric acid, but this time we're not adding it to a buffer, we're adding it to 1 liter of pure water. So here is our beaker that contains 1 liter of pure water. It has a pH of 7.00. This is not a buffer. And here comes that small amount of strong acid, which is going to be 0.040 moles of the hydronium ion. Now, when that's added to this sample of pure water, it says, assume that the final volume of the solution remains constant at 1 liter. We now have 0.040 moles of the hydronium ion dissolved in a total volume of 1 liter. So what you can see there underneath that beaker on the right is the concentration of the hydronium ion, 0.040 moles per liter. Now, how do we get the pH? We take the negative log of the hydronium ion concentration. And the negative log of 0.040 is 1.40. So the pH decreases not by a small amount, but by a very large amount. The pH decreases from 7 all the way down to 1.4, but of course, water is not a buffer. There's nothing to keep the pH relatively constant. If you just have water, you don't have a buffer. So I'm going to summarize on this next slide the difference between a buffer and pure water. So you can see at the top of this slide, if we start with a buffer solution, such as an equimolar amount of acetic acid and acetate, the pH initially is 4.74. Now, when 0.040 mole of the hydronium ion is added to that buffer, the pH did go down, but only by a small amount. The pH decreased from 4.74 to 4.70. So that's a good buffer, maintaining a relatively constant pH. But if we add that same amount of the hydronium ion, 0.040 mole of the hydronium ion, to pure water, which is not a buffer, then the pH decreases by a large amount, from 7 all the way down to 1.4. So this illustrates the power of a buffer to maintain a relatively constant pH when a small amount of a strong acid is added to the buffer. Now, in the next part of this question, we're going to take a look at what happens when a small amount of a strong base is added to a buffer. So let's go ahead and take a look at part F. So this is part F. It says write the net ionic equation for the reaction that occurs when potassium hydroxide, or any strong base, is added to this buffer solution. Remember that there are two components in this buffer solution, acetic acid and acetate. Since we're adding a strong base, we want an acid-base reaction to occur between the hydroxide ion and the weak acid. So acetic acid will react with the hydroxide ion, and the product of the reaction is the acetate ion and water. Now, looking at the equation that was written in part F, we can answer part G. So when a small amount of a strong base, like potassium hydroxide, is added to this buffer solution, the concentration of acetic acid will decrease, and you can see in part F that it's a reactant that's being consumed in that equation, and the concentration of the acetate ion will increase, and you can see in part F that it's being produced as a product in that equation. Now, as we move on to part H of this question, this will be very similar to what we had done back in part D of this question. So we have our rice table, we have our reaction filled in the top row of the rice table, but this time it's the reaction between hydroxide ions, not hydronium ions. So hydroxide ions are reacting with acetic acid to produce acetate and water. Now we have 4 milliliters of a 10 molar solution of potassium hydroxide. And when you do the calculation to determine the number of moles of hydroxide, it will be 0.004 liters times 10 moles per liter. And we get 0.040 moles of hydroxide. So same number of moles that we had of hydronium ions back in part D. Okay, what's going to happen in the change row of the rice table is that the acetic acid will decrease by a small amount, and it's going to be based on that limiting reactant. The hydroxide ion is the limiting reactant. So decrease by 0.040. The hydroxide ion concentration, or the amount of moles, will decrease by 0.040. But then on the other side of the equation, the number of moles of the acetate ion will increase by 0.040. Now, in the end of our rice table, it's going to be the difference. So 1 minus 0.04 is 0.96 moles of acetic acid, and the number of moles of the hydroxide ion decrease to a value which is essentially 0. And on the other side of the equation, we have an increase from 1 plus 0.04, so the number of moles of acetate ions would be 1.04 moles. And this is in a 1 liter solution. It says assume that the final volume of the solution remains constant at 1 liter. So concentration of acetic acid decreased a little bit. So now it is 0.96 moles per liter. Concentration of the acetate ion increased a little bit to 1.04 moles per liter. We're expecting the pH to go up, but only by a small amount. We're trying to keep the ratio If we can keep the ratio of acetate to acetic acid relatively constant, then the pH should remain relatively constant. Let's go ahead and plug in the 0.96 on the bottom of this Ka expression and 1.04 in the top of this Ka expression. So we plugged in the values for the concentration of acetate and acetic acid. Let's now rearrange this equation to solve for the concentration of the hydronium ion. So I'm going to go ahead and multiply both sides of this equation by 0.96 and then divide both sides of this equation by 1.04. And the concentration of the hydronium ion is based on the following calculation. 1.8 times 10 to the negative 5, which is the Ka, times 0.96 divided by 1.04. And when we do that math, we get 1.7 times 10 to the negative 5 moles per liter. That is our concentration of the hydronium ion. So all we have to do now is take the negative log of this number and find out what is our pH after this small amount of strong base potassium hydroxide was added. So the negative log of 1.7 times 10 to the negative 5 is 4.77. So this buffer had a pH of 4.74 before the strong base was added. Now it has a pH of 4.77. So it increased, but only by a very small amount. That's the power of a buffer. It maintains a relatively constant pH value. And again, based on this ratio that I'm highlighting on this slide, if you can keep the ratio of acetate to acetic acid, as in the conjugate base to the weak acid, if you keep that ratio relatively constant, then your pH will not change very much. So we changed from a 1-to-1 ratio. Now that ratio is 1.04 over 0.96. So it didn't change very much. All right, well, we added a strong base to a buffer. Now, in part I, suppose we had added that same amount of strong base to pure water instead of to a buffer. So we have our beaker that contains 1 liter of pure water. Here comes that small amount of hydroxide ion, the 4 milliliters of 10 molar potassium hydroxide. We are expecting the pH to increase by a much larger amount because water is not a buffer. So as we consider the 1 liter, it says assume that the final volume of the solution is 1 liter. The concentration of the hydroxide ion in that solution now is 0.040 moles of hydroxide per liter. We're two steps away from figuring out the pH. First, let's negative log 0.040, which is the concentration of hydroxide, and that gives us the pOH, not the pH, but the pOH. We get 1.40. Then if we do 14 minus the pOH, so 14 minus 1.40, what happened to our pH is it was 7, and now it's 12.6. So because water is not a buffer, the pH increases by a very large amount. And just like I did before, I'm going to go ahead and summarize on this slide what happened when we added a small amount of a strong base to a buffer solution versus to pure water. So in the buffer, we had an initial pH of 4.74, and that buffer contained an equimolar mixture of acetic acid and acetate. And so it behaved as a good buffer by keeping the pH relatively constant. The pH increased only by a small amount from 4.74 to 4.77. But when that same amount of hydroxide, 0.040 moles of hydroxide, was added to pure water, a much larger increase in pH from 7 to 12.60. So again, illustrating the power of a buffer to maintain a relatively constant pH when either a small amount of a strong acid or a small amount of a strong base is added to this buffer. The pH was able to stay relatively constant for this buffer. All right, now let's take a look at questions 10 and 11 in which we can consider how do we prepare a buffer. Now, in questions 10 and 11, we're going to take a look at various ways in which a buffer solution can be prepared. In question 10, it says the pKa of HNO2, which is nitrous acid, is 3.40. Select all of the following descriptions that would result in the formation of a buffer with a pH of 3.40. So if we're trying to make a buffer solution in which the pH of the buffer solution is equal to the pKa of the weak acid, then in this buffer solution, the concentration of nitrous acid, or HNO2, should be equal to the concentration of the nitrite ion, or NO2-. So there are 6 different descriptions in question 10. Let's analyze each of these descriptions and decide if it will result in a solution in which the concentration of HNO2 is equal to the concentration of NO2-. In our first description, we have 100 milliliters of 1.0 molar nitrous acid combined with 100 milliliters of 1.0 molar potassium nitrite. So that means if we have equal volumes and the same concentration, one of the solutions contains HNO2, the other solution contains NO2-. So yes, this would result in a buffer solution where there are equimolar amounts of HNO2, the weak acid, and NO2-, the conjugate base, so the pH would be equal to the pKa, which is 3.40. Now, in our next description, we're combining 100 milliliters of 1 molar HNO2, or nitrous acid, with 100 milliliters of 1 molar KOH, or potassium hydroxide. That is a strong base. So we have equal number of moles. We have 0.1 moles of nitrous acid and 0.1 moles of the hydroxide ion. What happens when this weak acid is combined with an equimolar amount of a strong base? The chemical reaction that would take place would convert all of the HNO2 into NO2-. If this sounds like a titration experiment, then yes, it is, but it would go all the way from the beginning to the equivalence point. So if we have the same number of moles of hydroxide as we have moles of the weak acid, then there would not be a mixture. There would be simply mostly NO2-, but not an equimolar mixture of HNO2 and NO2-. So that would not result in that appropriate buffer solution. In our next description, we're combining 100 milliliters of 1 molar HNO2, or nitrous acid, with 100 milliliters of 1 molar HNO3. That's nitric acid, which is one of the 6 strong acids. So you're not going to make a good buffer solution by combining a weak acid with a strong acid. So that would not result in the buffer that we're looking for. In the next description, we have details that appear similar to the first description. We are combining a solution of 1 molar nitrous acid with a solution of 1 molar potassium nitrite. The difference between this description and the first description in question 10 is that the volume of each solution is not the same. So we have 200 milliliters, or 0.2 liters, of 1 molar nitrous acid, and it's combined with 100 milliliters, or 0.1 liters, of 1 molar potassium nitrite. So this would make a buffer solution, but because we have 0.2 moles of nitrous acid, the weak acid, and we have 0.1 moles of NO2-, the conjugate base, then the concentration of HNO2 would be greater than the concentration of NO2- in this buffer solution. So it would make a buffer solution, but it would not have a pH of exactly 3.40 because the concentration of the weak acid is greater than the concentration of the conjugate base. In this buffer solution, the pH would be less than the pKa. So not the specific buffer that we're looking for. Now, in our next description, this one looks similar to the second description in that we're combining 1 molar nitrous acid with 1 molar potassium hydroxide, but the volumes are not the same. Take a look. What happens if we have 0.2 moles of nitrous acid combined with 0.1 moles of hydroxide? We're not going to convert all of the nitrous acid into the nitrite ion as we saw earlier in that second description. Now we're going to be converting half of the number of moles of nitrous acid into the nitrite ion, or the conjugate base. So does this sound like a titration experiment? Yes, but it sounds like the one that we're looking for, in that it would be getting us not all the way to the equivalence point, but to the half equivalence point. So because we have half the number of moles of hydroxide compared to the number of moles of nitrous acid, it would result in a mixture in which the concentration of nitrous acid would be equal to the concentration of the nitrite ion. So yes, this would result in the appropriate buffer that we're looking for. And then in our last description in question 10, if you combine a weak acid, HNO2, with a strong acid, HNO3, that would not result in the buffer solution that we're looking for. So hopefully all of those descriptions and my analysis of those make sense. Question 11 is similar to question 10. We just have a different buffer system to analyze. In question 11, it says the pKa of NH4+, which is the ammonium ion, is 9.26. Select all of the following descriptions that would result in the formation of a buffer with a pH of 9.26. So just like in question 10, we're looking for a buffer solution in which the pH of the buffer solution is equal to the pKa of the acid. So for our buffer solution, we would like the concentration of the ammonium ion, or NH4+, to be equal to the concentration of its conjugate base, and that would be NH3, or ammonia. So we have 6 descriptions. We'll analyze each description one at a time, and we'll see if it results in a solution in which the concentration of NH4+ is equal to the concentration of NH3. In our first description, we have 100 milliliters of 1 molar ammonia combined with 100 milliliters of 1 molar ammonium nitrate. So in the first solution, we have ammonia. In the second solution, we have a compound, ammonium nitrate, that contains the ammonium ion. Equal volumes, equal concentrations. So yes, in this solution, there would be equimolar amounts of both ammonia and ammonium, and so the pH would equal the pKa. This is the buffer solution that we're looking for. In the next description, we're combining 100 milliliters of 1 molar ammonia with 100 milliliters of 1 molar nitric acid, HNO3. So we're combining a weak base with a strong acid. Same volume, same concentration, so we have the same number of moles. What would happen if 0.1 mole of ammonia is combined with 0.1 mole of a strong acid, or the hydronium ion? You would get an acid-base reaction between the weak base, ammonia, and the hydronium ion to produce NH4+, or ammonium, and water. But the problem is that it would convert all of the ammonia into the ammonium ion. This sounds like an acid-base titration, but it sounds like it goes all the way to the equivalence point. So we have the same number of moles of the strong acid, or the hydronium ion, as we have moles of the weak base. This would not get us to the half equivalence point. This would get us all the way to the equivalence point. This would not give us an equal mixture of NH3 and NH4+. In our next example, we have 100 milliliters of 1 molar ammonia and 100 milliliters of 1 molar potassium hydroxide, which is a strong base. We're not going to get the buffer that we're looking for by combining a weak base with a strong base. So we're trying to find a solution in which the NH4+ is equal to the NH3, and this would not happen. In our next example, we start with 200 milliliters of 1 molar ammonia and 100 milliliters of 1 molar ammonium nitrate. So this would result in a buffer solution, but it's not the buffer solution that we're looking for. And the reason why is that 200 milliliters, or 0.2 liters, of 1 molar ammonia and 100 milliliters of, or 0.1 liters of 1 molar ammonium nitrate, we're going to get a different number of moles for the components of this buffer. We have 0.2 mole of ammonia and 0.1 mole of ammonium. It would make a buffer solution, but since the concentration of the weak base is greater than the concentration of its conjugate acid, the pH would not be equal to the pKa, but instead the pH would be greater than the pKa. So it is a buffer solution, but it's not the buffer solution that we're looking for. In our next description, this looks similar to the second description that was listed, where we have the weak base ammonia combined with the strong acid, nitric acid. but this time the volumes and therefore the number of moles are different. So we have 200 milliliters or 0.2 liters of 1 molar ammonia, and we have 100 milliliters or 0.1 liters of 1 molar nitric acid, a strong acid. So what happens if we have 0.2 mole of ammonia combined with 0.1 mole of a strong acid, or the hydronium ion? We're going to get that acid-base titration, but instead of converting all of the ammonia into the NH4 plus ion, in this example we're going to convert half of the number of moles of ammonia into moles of NH4 plus. So this would result in a similar situation to the half equivalence point in a titration. Because the number of mole of the strong acid, or the hydronium ion, is half as much as the number of moles of the weak base, then this would result in a buffer solution where we have an equal amount of NH3 and NH4 plus. In our last example, we're combining a weak base and a strong base. This would not result in the buffer that we're looking for, so that would not give us an equal amount of NH4 plus and NH3. Now, we've answered questions 10 and 11. Let me go ahead and summarize. There are 4 possible combinations that should result in the formation of a buffer solution, where HA represents a weak acid and A- represents its conjugate base, and the letter B represents a weak base and HB plus represents its conjugate acid. In the first example shown in this table, you could combine the weak acid with its conjugate base in a 1-to-1 mole ratio. The next example says you could combine a weak acid with a strong base, but combine them in such a way that the number of moles of the hydroxide ion is half as much as the number of moles of the weak acid. This would result in that half equivalence point situation, resulting in an equal mixture of both HA and A-. In our next example in the table, you could combine the weak base and the conjugate acid in a 1-to-1 mole ratio. And then the last example listed in this table is you could combine the weak base and a strong acid in a mole ratio such that the number of moles of the strong acid, or the hydronium ion, are half as much as the number of moles of the weak base, again resulting in that half equivalence point situation where you have an equal amount of both the weak base and its conjugate acid. All right, now we are ready to move on in the packet to our next topic. This is topic 8.9, Henderson-Hasselbalch equation. Here is an essential knowledge statement from the AP Chemistry course and exam description. The pH of the buffer is related to the pKa of the acid and the concentration ratio of the conjugate acid-base pair. This relation is a consequence of the equilibrium expression associated with the dissociation of a weak acid and is described by the Henderson-Hasselbalch equation. Adding small amounts of acid or base to a buffered solution does not significantly change the ratio of A- to HA, and thus does not significantly change the solution pH. The change in pH on addition of acid or base to a buffered solution is therefore much less than it would have been in the absence of the buffer. And this equation, which is known as the Henderson-Hasselbalch equation, is pH is equal to the pKa plus the log of the ratio of the concentration of A- divided by the concentration of the weak acid, or HA. And you can see, if you look on the AP Chemistry equations and constant sheet, that in addition to the many equations that involve pH, pOH, and acids and bases, the Henderson-Hasselbalch equation is included on the AP Chemistry equation sheet. All right, this is question 12 in the packet. It says 3 different buffer solutions are prepared by combining solutions of HF, or hydrofluoric acid, and NaF, or sodium fluoride, as described in the table below. So in the table, there are 3 different buffer solutions, and we are given the data for the concentration of hydrofluoric acid in the buffer and the concentration of sodium fluoride in the buffer. So part A says to calculate the pH of each buffer solution in the table above by using the Ka expression for hydrofluoric acid. So let's substitute the concentration of the fluoride ion on the top and the concentration of hydrofluoric acid on the bottom. And when these concentrations are both 1 and 1, that means that they cancel out, such that the concentration of the hydronium ion is equal to the Ka, which is 6.8 times 10 to the negative 4. And now we take the negative log of the concentration of the hydronium ion. The negative log of 6.8 times 10 to the negative 4 gives us a pH value of 3.17. Now, in buffer number 2, the concentration of fluoride is 2 molar, and the concentration of hydrofluoric acid is 1 molar. So we plug in those values for concentration into the Ka expression. Now we have to solve for the concentration of the hydronium ion. It's going to be 6.8 times 10 to the negative 4 divided by 2. And so we get 3.4 times 10 to the negative 4 moles per liter. We take the negative log of the concentration of hydronium to get the pH, and this works out to be a pH of 3.47. Now in the third buffer, we put 2 molar for the concentration of HF on the bottom and 1 molar for the concentration of the fluoride ion on the top. Now we have to solve for the concentration of the hydronium ion, and that will equal 6.8 times 10 to the negative 4 times 2. So we do that math and we get 1.36 times 10 to the negative 3 moles per liter. This is the concentration of the hydronium ion. Let's take the negative log to get the pH. And so the negative log of 1.36 times 10 to the negative 3 is 2.87. Now, as we go on to part B of question 12, we see that we're still going to calculate the pH of each buffer solution in the table above, but this time we're going to use the Henderson-Hasselbalch equation to do that calculation. So here is the Henderson-Hasselbalch equation. pH equals pKa plus the log of the ratio of concentration of A minus over concentration of HA. So for this particular buffer, that would be concentration of fluoride over concentration of hydrofluoric acid. The negative log of the Ka value gives us the pKa, and that works out to be 3.17. And since we have a concentration of HF and F minus that are the same, that means that the log of 1 on your calculator works out to be 0. So 3.17 plus 0 gives us 3.17. Now moving on to buffer number 2, we have a different concentration for HF and F minus. So let's plug in the concentration of F minus on the top, which is 2, and the concentration of HF on the bottom, which is 1. Now it's going to be 3.17 plus the log of 2. So 3.17 plus the log of 2 gives us 3.17 plus 0.30, and that works out to be a pH of 3.47. And now for buffer 3, the ratio of F minus over HF would be 1 over 2. So we have the concentration of F minus, which is 1 molar, the concentration of HF, which is 2 molar. So it's going to be 3.17 plus the log of 1/2. So 3.17 plus negative 0.30 gives us a value of 2.87. Now, when you compare your answers to part A and part B, you realize that you get the same pH for all 3 buffer solutions in the table above. But in part A, we did not need the Henderson-Hasselbalch equation. We simply used the Ka expression. So the Henderson-Hasselbalch equation is useful, but it's not necessary to calculate the pH of a buffer solution. You can use the Ka expression and plug in the appropriate concentrations, solve for the concentration of the hydronium ion, and then take the negative log to get the pH. All right, let's move on to part C of question 12. It says a particulate representation of a small portion of buffer number 1 is shown below. Water molecules and sodium ions are not shown. In the boxes below, draw diagrams to represent the components of buffer number 2 and buffer number 3. Represent HF molecules and F minus ions as indicated below. So from the information in the table, we see that for buffer number 1, the concentration of HF is equal to the concentration of F minus. And that's what we see represented in that first particulate diagram for buffer number 1. We see 6 HF molecules and 6 F- ions. Now, moving on to buffer number 2, we can see from the information in the table that the concentration of F- is twice as much as the concentration of HF. So therefore, the particulate diagram should represent that the number of particles of F- should be twice as much as the number of particles of HF. So to draw that diagram, we can use 8 F- ions and 4 HF molecules. So something like this: 8 F- ions and 4 HF molecules. Now moving on to buffer number 3, it's going to be reversed. So in buffer number 3, the concentration of HF should be twice as much as the concentration of F-. So in the particulate diagram, there should be a greater number of HF as compared to F-. If we have 8 HF molecules and 4 F- ions, then that will demonstrate that the concentration of HF is twice as much as the concentration of F-. So 8 HF molecules and 4 F- ions. Now let's take a look at question 13 in the packet. It says formic acid, which is HCO2H, ionizes in aqueous solution according to the chemical equation shown above. So in the equation, we have a molecule of HCO2H, or formic acid, reacting with water to produce the ion HCO2-, which is the conjugate base known as the formate ion, and also producing the hydronium ion H3O+. We are given the Ka expression for formic acid, and the value of Ka is 1.8 times 10 to the negative 4. We're also given the Henderson-Hasselbalch equation, in which we have pH equals pKa plus the log of the ratio of the concentration of the formate ion over the concentration of formic acid. It says that we can use either the Ka expression for formic acid or the Henderson-Hasselbalch equation to fill in the missing information in the table below. So what I will do in this video is I will show you both ways of calculating the missing information. So when we use the Henderson-Hasselbalch equation, we need to calculate the pKa for the acid. So for formic acid, the pKa would be the negative log of 1.8 times 10 to the negative 4, and that works out to be 3.74. So now we have that value when we need it. You can see in solution 1 that the concentration of formic acid, so HCO2H, is equal to the concentration of the formate ion, which is the conjugate base, HCO2-. So when we have the pH equal to the pKa of 3.74, the concentration of the acid is equal to the concentration of the base. Now for solutions 2, 3, and 4, those concentrations are not going to be equal to each other. So I'll start with solution 2, and I'm going to use the Ka expression. I will also use the Henderson-Hasselbalch equation. So the concentration of the formate ion, which is HCO2-, is 1.35 molar, and that is greater than the concentration of formic acid, which is 0.750 molar. So when the concentration of the conjugate base is greater than the concentration of the weak acid, we know that the pH should be greater than the pKa. So we're expecting the pH for solution 2 to be higher than 3.74. The ratio of 1.35 divided by 0.75 is 1.80. And now I'll use the Ka expression. I'm going to plug in 1.35 for the concentration of the formate ion on the top, and I'll plug in 0.750 for the concentration of formic acid on the bottom. Now I have to rearrange this equation to solve for the concentration of the hydronium ion. And when I do that, I get 1.8 times 10 to the negative 4 times 0.750 divided by 1.35. And when I do that math, I get that the concentration of the hydronium ion is 1 times 10 to the negative 4. The negative log of that concentration of the hydronium ion is the pH of solution 2. And that's going to work out to be a pH of 4.00. Now, I will use the Henderson-Hasselbalch equation, and we should get the same answer. So I'll use the Henderson-Hasselbalch equation, And so it's going to be 3.74 plus the log of that ratio, which is 1.80. And when you do that math, you get 3.74 plus 0.26, which is equal to 4.00. So we got the same answer for the pH of solution 2 by using either the Ka expression or using the Henderson-Hasselbalch equation. Now let's move on to solution 3. With solution 3, we can see that a pH of 3.52 is less than a pH of 3.74. This means that the pH is less than the pKa. And when the pH is less than the pKa, that means that the concentration of formic acid should be greater than the concentration of the formate ion. That's our prediction. Now, since we already know the pH, then the inverse of that to figure out the concentration of the hydronium ion would be 10 to the minus pH. So 10 to the minus 3.52 gives us the concentration of the hydronium ion. Now, let's put that number into the Ka expression. So here is our Ka expression, and I've plugged in the concentration of the hydronium ion, which I got from the pH. I'm going to plug in a concentration of the formate ion on the top, which is 1.00 molar. And since I don't know the concentration of formic acid on the bottom, that's the quantity that I am solving for. So I rearrange the equation, and the concentration of formic acid is equal to 3 times 10 to the negative 4 times 1 divided by the Ka, which is 1.8 times 10 to the negative 4. And when I do that math, I get 1.67 moles per liter. The ratio would be 1 divided by 1.67, which works out to be 0.60. Now I'm going to go ahead and solve for that information for solution 3 using the Henderson-Hasselbalch equation. So I'm going to plug in what I know into the Henderson-Hasselbalch equation. So we have pH, which is 3.52, plus the pKa, which is 3.74, plus the log of this ratio of concentration of formate divided by concentration of formic acid. Now, since I don't know what that is, I'm solving for it. The log of that ratio is equal to 3.52 minus 3.74, which works out to be negative 0.22. Now I'm going to do 10, the number 10, raised to the minus 0.22, and this will give me the value of that ratio. So that ratio works out to be 0.60 because 10 to the minus 0.22 is equal to that value. Now to figure out the concentration of formic acid, it's going to be, just looking at the math, 1 divided by x equals 0.60, so therefore x equals 1 divided by 0.6, and that works out to be 1.67. So now I have done the calculations for solution 3 using both the Ka expression and the Henderson-Hasselbalch equation. We got the same answer either way. Moving on to solution 4, we know that the pH is 3.82, which is greater than the pKa of 3.74, so our prediction is that there should be a greater concentration of the conjugate base compared to the concentration of the acid because the pH is greater than the pKa. I can take the inverse of the pH by doing 10 to the minus pH to get me the concentration of the hydronium ion. So the concentration of the hydronium ion in solution 4 is 10 to the minus 3.82, and that works out to be 1.5 times 10 to the negative 4 moles per liter. I'm going to plug that value in to the Ka expression. So I have the concentration of the hydronium ion on the top. I don't know the concentration of the formate ion, so that's unknown. And on the bottom, the concentration of formic acid is also 1.00 molar, so I can plug that number in. I'm going to solve for the concentration of HCO2 minus, and I do the rearranging of the equation. I get 1.8 times 10 to the negative 4 times 1 divided by 1.5 times 10 to the negative 4. And when I do that math, it works out to be 1.20 moles per liter. So the ratio of formate concentration divided by formic acid concentration is 1.20. Now I will use the Henderson-Hasselbalch equation to do those same calculations for solution 4. So I'll start with the Henderson-Hasselbalch equation. pH of 3.82 is equal to the pKa of 3.74 plus the log of that ratio. So 3.82 minus 3.74 gives me a value of 0.08. So the log of that ratio is equal to 0.08. 10, the number 10, to the 0.08 gives me a value of 1.20. So that is the value of the ratio, and that means that since it's concentration of formate divided by concentration of formic acid, which is 1, then the concentration of formate must be 1.20 moles per liter. So in question 13, I was showing you that you can use either the Ka expression or the Henderson-Hasselbalch equation to solve for the missing quantities in this table. Now it's time to move on to our next topic. This is the last topic in Unit 8, the last topic in this packet, and this is topic 8.10, buffer capacity. Here are some essential knowledge statements from the AP Chemistry course and exam description. Increasing the concentration of the buffer components while keeping the ratio of these concentrations constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. When a buffer has more conjugate acid than base, it has a greater buffer capacity for the addition of added base than acid. When a buffer has more conjugate base than acid, it has a greater buffer capacity for addition of added acid than base. All right, this is question 14 in the packet. It says 2 different buffer solutions are prepared by combining solutions of acetic acid, HC2H3O2, and sodium acetate, NaC2H3O2, as described in the table below. The Ka for acetic acid is 1.8 times 10 to the negative 5. So for buffer number 1, the concentration of acetic acid is 1 molar, and the concentration of sodium acetate is also 1 molar. For buffer number 2, the concentration of acetic acid is much smaller, it's 0.05 molar, and the concentration of sodium acetate is also that same smaller number of 0.05 molar. So part A, calculate the pH of each buffer solution in the table above. We see that in each buffer solution there are equimolar amounts of acetic acid and acetate. Therefore, the pH of each buffer solution is equal to the pKa, which is the negative log of 1.8 times 10 to the negative 5. That means that each buffer solution has a pH of 4.74. Now let's take a look at part B of this question. It says a sample of 0.045 moles of nitric acid, which is a strong acid, is added to 1 liter of buffer number 1. Assume that the change in volume of the solution is negligible. Use the Rice table to help you calculate the pH of the solution after the nitric acid is added. So in our Rice table, we have a reaction, and this is the reaction that would occur if a small amount of a strong acid is added to this buffer. So the 2 components of the buffer are acetic acid and acetate. So when a small amount of a strong acid is added to this buffer, it's going to be the acetate ion reacting with the strong acid in the form of the hydronium ion to produce acetic acid and water. Since we have 1 liter of a 1 molar solution of each component of the buffer, that's why the number 1.00 mole has already been filled in. And we have 0.045 mole of that strong acid, so we're showing that's the number of moles of the hydronium ion that's being added. Since the hydronium ion, the 0.045 mole, that's our limiting reactant, that's going to determine the change in the next row of this Rice table. So the number of moles of the acetate ion is going to decrease by 0.045 moles. The number of moles of the hydronium ion will also decrease by that same amount. And the number of moles of acetic acid will increase by 0.045 mole. So now at the end of our Rice table, we have 1 minus 0.045, which gives us the moles for the acetate ion, and that works out to be 0.955. Our number of moles of the hydronium ion has essentially decreased to 0. It's a very small number. And for the acetic acid, it's going to be 1 plus 0.045. So 1.045. Since we can assume that the change in the volume of the solution is negligible, we still have 1 liter of this buffer solution. So the number of moles is the same as the concentration, moles per liter. So concentration of acetate is going to be 0.955. Concentration of acetic acid is going to be 1.045. Those numbers for concentration of acetate and acetic acid will now be plugged in to the Ka expression. So I have concentration of hydronium, which I don't know, times 0.955 divided by 1.045. Now let's solve for the concentration of the hydronium ion, and that works out to be 1.8 times 10 to the negative 5 times 1.045 divided by 0.955. When we do this math, we get the concentration of the hydronium ion is 2 times 10 to the negative 5. Let's take the negative log of that number to get the pH, and it works out to be a pH of 4.70. As a result of adding a small amount of a strong acid to this buffer, the pH decreased from a value of 4.74 to 4.70. Now we're going to take a look in part C of this question. What happens if we add that same amount of strong acid, that 0.045 mole of strong acid, to 1 liter of buffer 2? Now buffer number 2, it has the same pH as buffer number 1, but the concentration of the buffer components is smaller. So we're going to see what happens when we have a smaller concentration of the buffer components. I'll go ahead and fill in the change row of the rice table with minus 0.045, minus 0.045, and plus 0.045. So now for the acetate ion, at the end of the rice table, it's going to be 0.05 minus 0.045, and that works out to be 0.005 moles. The concentration or the amount of the hydronium ion has gone down to a very small number, so it's essentially 0. And for the acetic acid, it's going to be 0.05 plus 0.045. That works out to be 0.095. We can assume we have 1 liter of solution, so the number of moles is also the same as the concentration. Let's plug in those values into the Ka expression and solve for the concentration of the hydronium ion. So we have 0.005 on the top for the concentration of the acetate ion, and 0.095 on the bottom for the concentration of acetic acid. So the concentration of the hydronium ion works out to be 1.8 times 10 to the negative 5 times 0.095 divided by 0.005. When we do this math, we get 3.4 times 10 to the negative 4. Let's take the negative log of that number to get the pH, and we get a pH of 3.47. So now that we finished analyzing the results about what happened to the pH of each buffer, let's move on to parts D and E of this question so we can compare what happened for buffer number 1 with what happened for buffer number 2 and make a conclusion about the relative buffer capacity. So with buffer number 1, we can see from the table it had a higher concentration of each buffer component. The initial pH was 4.74, and after a small amount of a strong acid was added to this buffer, the final pH decreased to a value of 4.70, so it decreased by a rather small amount. Now with buffer number 2, it had a much smaller concentration of each buffer component. The initial pH of buffer number 2 was the same as buffer number 1, but when that same small amount of strong acid, that 0.045 mole of nitric acid, was added to buffer number 2, it experienced a much larger magnitude of change for its pH. It went from 4.74 all the way down to 3.47. Let's answer part D. It says, which buffer solution, number 1 or number 2, experienced a greater change in pH after the addition of 0.045 mole of nitric acid? So based on the data, that would be buffer number 2. Part E, Which buffer solution, number 1 or number 2, has the greater buffer capacity? This can be determined in two ways. One, it has a larger concentration of each buffer component. That's definitely buffer number 1. But another consequence of having a greater buffer capacity is that it experiences a smaller change in pH. Let's go back to that essential knowledge statement for topic 8.10. Increasing the concentration of the buffer components while keeping the ratio of these concentrations constant keeps the pH of the buffer the same, but increases the capacity of the buffer to neutralize added acid or base. In other words, it will increase the likelihood that the change in pH will be rather small when a small amount of a strong acid or base is added to it. All right, now let's move on to our next question in the packet, which is question 15. In question 15, it says 2 different buffer solutions are prepared by combining solutions of ammonia, which is NH3, and ammonium nitrate, which is NH4NO3. A sample of sodium hydroxide is added to each buffer solution. The solutions are mixed thoroughly, and the pH is recorded. The data from the experiment are recorded in the table below. So we have buffer number 1, which contains NH3 and NH4+. We have buffer number 2, which also contains those same buffer components. The volume of each buffer is the same, it's 1 liter. The initial pH of each buffer is the same, it's 9.26. And the number of moles of sodium hydroxide that was added to each buffer is the same, it's 0.10 moles. So let's see what happened to the final pH of the buffer. For buffer number 1, the pH increased from 9.26 to 9.35. For buffer number 2, the pH also increased, but it increased by a larger magnitude. It went from 9.26 to 9.96. So we don't have to know actually the initial concentration of ammonia and ammonium to actually make the following conclusion, that buffer number 1 must have had the greater buffer capacity. Why? Because it experienced a smaller change in pH. So buffer number 1 must have been able to absorb this added sodium hydroxide and keep that ratio from changing too much. So which buffer solution, number 1 or number 2, has the greater buffer capacity? Justify your answer in terms of the data in the table above. So each buffer solution has the same volume, the same buffer components, the same amount of moles of sodium hydroxide were added to each buffer. But buffer number 1 has the greater buffer capacity because it experienced a smaller magnitude of change in pH. All right, now let's take a look at question 16. This is the last question in the packet, and it says, 2 different buffer solutions are prepared by combining solutions of nitrous acid, HNO2, and potassium nitrite, KNO2, as described in the table below. So for buffer number 1, the concentration of nitrous acid is 1.50 molar, and the concentration of potassium nitrite is 1 molar. So we have a higher concentration of the acid as compared to the conjugate base. In buffer number 2, it's been flipped around. Now, the concentration of the NO2-, the conjugate base, is greater than the concentration of the weak acid, HNO2. Part A. Buffer number 1 has a greater buffer capacity for the addition of added, and we have to circle one of those words, because it contains a higher concentration of, and that would be HNO2. We can see that 1.5 molar is greater than 1 molar. So if it has a higher concentration of acid, then it's going to have a greater buffer capacity for the addition of added base. Again, here's that essential knowledge statement. When a buffer has more conjugate acid than base, it has a greater buffer capacity for the addition of added base than acid. Now let's flip it around for buffer number 2. This is part B. Buffer number 2 has a greater buffer capacity for the addition of added, and we have to circle that word, because it has a higher concentration of, and that would be NO2-. We can see that 1.5 molar for the potassium nitrite is greater than 1 molar for the nitrous acid. So if it has a higher concentration of the conjugate base, it will have a greater buffer capacity for the addition of added acid. Again, here's that essential knowledge statement. When a buffer has more conjugate base than acid, it has a greater buffer capacity for the addition of added acid than base. Now we're going to move on to the last topic in this packet. This is topic 8.11, pH and solubility. Here is an essential knowledge statement from the AP Chemistry course and exam description. The solubility of a salt is pH sensitive when one of the constituent ions is a weak acid, a weak base, or the hydroxide ion. And these effects can be understood qualitatively using Le Chatelier's principle. Now let's take a look at question 17. Question 17 says the following. The dissolution of solid magnesium hydroxide in water is represented by the equation above. A saturated solution is prepared in a beaker at 25 degrees Celsius by adding excess solid magnesium hydroxide to distilled water and stirring until no more solid dissolves. Part A. Several drops of concentrated aqueous sodium hydroxide are added to a saturated solution of magnesium hydroxide, and the mixture is stirred thoroughly. Assume that the change in volume is negligible and that the temperature remains constant at 25 degrees Celsius. The addition of aqueous sodium hydroxide causes the concentration of magnesium ions in the solution to decrease. Explain this result in terms of Le Chatelier's principle. Your explanation should also include a comparison of QSP and KSP at the moment that the aqueous sodium hydroxide is added to the solution. So the change that is being made to this solution of magnesium hydroxide is that sodium hydroxide is added to it. So adding a small amount of concentrated sodium hydroxide will cause the value of the concentration of hydroxide in the solution to increase. And notice that hydroxide is a product in this equation for the dissolution of magnesium hydroxide. Well, if you increase the concentration of a product, in this case, the hydroxide ion, then QSP becomes greater than KSP. When the concentration of hydroxide ions increase, Q becomes greater than K for this dissolution of magnesium hydroxide. Well, if Q becomes greater than K, then the equilibrium for the dissolution of magnesium hydroxide experiences a net conversion from products to reactants, or from right to left. And this will cause the concentration of magnesium ions to decrease. So to summarize what I said, the answer to number 17, part A, is the following. Adding aqueous sodium hydroxide to the saturated magnesium hydroxide solution causes the value of the concentration of the hydroxide ion to increase. As a result, QSP becomes greater than KSP, and there will be a net conversion of products to reactants, or a shift in the equilibrium from right to left. And the value for the concentration of the magnesium ion will decrease after aqueous sodium hydroxide is added. Now let's take a look at part B of this question. Now, part B of question 17 is similar to part A, but instead of adding sodium hydroxide to this saturated solution of magnesium hydroxide, so sodium hydroxide is a strong base, in part B we're adding a strong acid. So several drops of concentrated nitric acid are added to a saturated solution of magnesium hydroxide, and the mixture is stirred thoroughly. Assume that the change in volume is negligible and that the temperature remains constant at 25 degrees Celsius. Now, the addition of aqueous nitric acid causes the concentration of the magnesium ions in the solution to increase. So back in part A, when sodium hydroxide was added, the concentration of magnesium ions decreased. So we're kind of going in the opposite direction here, adding an acid instead of a base. So it says explain this result in terms of Le Chatelier's principle. Your explanation should also include a comparison of QSP and KSP at the moment that the aqueous nitric acid is added to the solution. So nitric acid is added, so adding a small amount of concentrated nitric acid will cause the value of the H plus ions, or the hydronium ions, in the solution to increase. Now you don't see any H plus ions in this equation for the dissolution of magnesium hydroxide. However, the H plus ions will affect the concentration of the hydroxide ions. So based on this acid-base reaction between H plus and OH minus to produce water, this will cause the value of the concentration of hydroxide to decrease. So the H plus ions from the strong acid react with and therefore consume some of the hydroxide ions. So the value for the concentration of hydroxide in this solution will decrease. And if you're decreasing the concentration of one of the products, QSP will now become less than KSP. So if the concentration of the hydroxide ions in solution decreases, then QSP becomes less than KSP. And the equilibrium for the dissolution of magnesium hydroxide will experience a net conversion from reactants to products, or from left to right. As a result, the concentration of the magnesium ions will increase. So in part A, sodium hydroxide was added, and in part B, nitric acid was added. Let me go ahead and summarize what I said in part B. So adding nitric acid to the saturated magnesium hydroxide solution causes the value of the concentration of the hydroxide ions to decrease because of this reaction between H plus and OH minus to produce water. Hydroxide ions will be consumed, so the concentration of hydroxide will decrease. QSP becomes less than KSP, and there will be a net conversion of reactants to products, or a shift in the equilibrium from left to right. And so the value for the concentration of the magnesium ion should increase after nitric acid is added. Now in part C, it's sort of a general summary of parts A and B of question 17. So it says the results in parts A and B can be summarized as follows. The solubility of magnesium hydroxide either decreases or increases, and we're talking about as the pH of the solution increases as opposed to as the pH of the solution decreases. So if you increase the pH, a higher pH means more hydroxide ions. And if the hydroxide ions increase, then Q becomes greater than K. So if QSP becomes greater than KSP, the solubility of magnesium hydroxide would decrease if additional hydroxide ions are added. In other words, if the pH of the solution increases. So on the other hand, if the pH of the solution decreases, now a lower pH means that H plus ions are increasing. And then hydroxide ions would decrease because of that reaction that consumes hydroxide. Well, if you decrease hydroxide, then QSP becomes less than KSP, and as a result, the solubility of magnesium hydroxide would increase as the pH decreases. So decreasing the solubility of magnesium hydroxide in the presence of a strong base, increasing the solubility of magnesium hydroxide in the presence of a strong acid. Now, as we move on to question 18 in this packet, it's very similar to question 17 because it also involves a metal hydroxide compound. So instead of magnesium hydroxide, take a look at question 18. It involves nickel hydroxide. So it's similar in that we have a dissolution of a metal hydroxide compound. All right, number 18 says the following. The dissolution of solid nickel hydroxide in water is represented by the equation above. A saturated solution is prepared in a beaker at 25 degrees Celsius by adding excess solid nickel hydroxide to distilled water and stirring until no more solid dissolves. The solubility of nickel hydroxide in water will be affected by changes in the pH of the solution. In part A, it says when a small amount of concentrated nitric acid, which is a strong acid, is added to a saturated solution of nickel hydroxide, the pH of the solution will, okay, so more strong acid means a lower pH, so decrease. And of course, a lower pH means more H plus ions, so an increase in the concentration of H plus, but as a result, a decrease in the concentration of hydroxide ions. So more H plus ions will react with and consume hydroxide ions. So the concentration of the hydroxide ions in the solution will decrease. As a result of this change, the value of QSP will become less than the value of KSP for nickel hydroxide. And the equilibrium for the dissolution of nickel hydroxide will experience a net conversion from left to right or from reactants to products. The solubility of the nickel hydroxide will increase when a strong acid such as nitric acid is added. Now on to part B. When a small amount of concentrated potassium hydroxide, which is a strong base, is added to a saturated solution of nickel hydroxide, more base means higher pH. So the pH of the solution will increase. Higher pH means more hydroxide ions. The concentration of the hydroxide ions in the solution will increase. As a result of this change, QSP will become greater than the value of KSP for nickel hydroxide. So the equilibrium for the dissolution of nickel hydroxide will experience a net conversion from right to left or from products to reactants. And the solubility of nickel hydroxide will decrease when a strong base such as potassium hydroxide is added. This is also an example of what's called the common ion effect that you learned about back in Unit 7. Topic 7.12 was called the common ion effect. So you're adding more hydroxide, and that increases the concentration of a common ion, and it shifts this equilibrium from right to left, or from products to reactants. All right, now let's take a look at question 19. Now, as you can see at the top of this slide, it says that question 19 in this packet was taken from free response question number 7 on the 2022 AP Chemistry exam. Free response questions and scoring information from past AP Chemistry exams can be found by visiting the following website, and you can see that listed on this slide. And just a warning that in question 19, which again came from a free response question, not all of the parts of this question are specific to Unit 8. Some of them might be review of topics that you learned in earlier units. But at the end of question 19, you will definitely see an example of topic 8.11, pH and solubility. Okay, let's take a look at part A. We are given a Lewis electron dot diagram of the oxalate ion, which has the chemical formula C2O42-. And part A says, identify the hybridization of the valence orbitals of either carbon atom in the oxalate ion. So here comes the review of things you had learned earlier. So back in Unit 2, Topic 2.7, VSEPR and hybridization, it says that the terms hybridization and hybrid atomic orbital are used to describe the arrangement of electrons around a central atom. So the answer to this question is either SP, SP2, or SP3. So I'm going to show you some things that I had mentioned in my earlier video for topic 2.7. And so these hybridization values of SP, SP2, and SP3 have to do with the number of electron domains. So 2 electron domains, SP hybridization, 3 electron domains, SP2 hybridization, or 4 electron domains, SP3. So here are some examples from my earlier video for topic 2.7. So 2 electron domains, SP, 3 electron domains, SP2, 4 electron domains, SP3. Now let's go back to that oxalate ion Lewis structure. So if we look at the oxalate ion, around either of these carbons, I can see exactly 3 electron domains. So therefore, the correct answer to number 19, part A, is going to be sp2. 3 electron domains around the central atom, sp2. And now I'm going to show you on this next slide, this is the official scoring guidelines from the 2022 AP Chemistry exam, question 7. So for part A, the correct answer was sp2. Now let's take a look at part B of this question. Part B talks about silver oxalate, so an ionic compound that is slightly soluble in water, and the value of Ksp for silver oxalate is 5.40 times 10 to the negative 12 at 25 degrees Celsius. So part I of part B says write the expression for the solubility product constant Ksp for the silver oxalate. Be careful to include the correct charges on your ions when you write the Ksp. Now we're already given that the charge on the oxalate ion is -2. So if I have 2 silver ions, they must have a charge of +1 each. So there is my solid silver oxalate. It will break up into 2 silver ions that have a charge of +1, and then 1 oxalate ion that has a charge of -2. And then the Ksp is equal to 5.40 times 10 to the negative 12. Let's write the Ksp expression. It's going to be concentration of silver times concentration of the oxalate ion, but don't forget to use that coefficient of 2 for the silver as an exponent. So there is my answer to part BI, and I'll go back and show you the official scoring guidelines from the 2022 AP Chemistry exam. So you can see Ksp equals concentration of Ag plus squared times concentration of C2O4 minus, the oxalate ion. All right, well, that's the answer to BI. Now let's take a look at part B double I. It says calculate the molar solubility of silver oxalate in neutral distilled water at 25 degrees Celsius. So we did this back in topic 7.11, talking about the solubility product or information about Ksp. So it's going to be X for the concentration of silver oxalate, X for the concentration of the oxalate ions in this saturated solution, and 2x for the concentration of the silver ions. I'm going to go ahead and plug in the 2x and the x as concentrations, and then we'll solve for that molar solubility for x. So 2x quantity squared times x is equal to the Ksp of 5.40 times 10 to the negative 12. And you may remember seeing in my Unit 7 videos involving solubility equilibria that when you have this 2-to-1 ratio of ions, you get 4x cubed for the math involved. So 5.40 times 10 to the negative 12 is equal to 4x cubed. I'm going to take the Ksp value, divide by 4, take the cube root so I can solve for x. So 5.40 times 10 to the negative 12 divided by 4, and then the cube root of that number gives me my answer. So that is the molar solubility in terms of x of the silver oxalate. So 1.11 times 10 to the negative 4 moles per liter. On the official scoring guidelines, you can see that same value, 1.11 times 10 to the negative 4 moles per liter, and they show how they got that. They said 4s cubed, where s is the solubility. Now, last part of this question, on to part B triple I. This is the one that deals with topic 8.11, pH and solubility. The molar solubility of silver oxalate increases when it is dissolved in 0.50 molar perchloric acid. So perchloric acid is one of the 6 strong acids that you should memorize for the AP Chemistry exam. So it's more soluble in the presence of a strong acid. Write the balanced net ionic equation for the process that occurs between species in solution that contributes to the increased solubility of silver oxalate in this strong acid, perchloric acid. Now, strong acid, perchloric acid, we're increasing the solubility just like we saw back in questions 17 and 18, we observed that the solubility of an ionic compound, it was a metal hydroxide, increases when a strong acid is added. So H plus ions had reacted with the hydroxide ions in magnesium hydroxide and nickel hydroxide, and that resulted in Q becoming less than K. So when QSP becomes less than KSP, the equilibrium for the dissolution of the solid will experience a net conversion from left to right, or from the solid to the aqueous ion. So we're increasing the solubility of either magnesium hydroxide or nickel hydroxide in the presence of a strong acid. Now, we don't see any hydroxide ions in the equation for the dissolution of silver oxalate, but let's focus on the fact that here comes the H plus ions from this strong acid. What could they possibly react with that would drive this equilibrium or shift this equilibrium from left to right? So what could the H plus ions react with? So which ion, Ag plus or C2O42 minus? Is it silver or oxalate that is more likely to undergo some sort of chemical reaction with H plus ions? So earlier we saw H plus reacting with OH minus to make water. So I would say that if anything's going to react with the H plus ions, it would be the negative ion. So not Ag plus reacting with H plus, but oxalate, C2O42 minus, reacting in kind of a similar way to hydroxide, acting as some sort of proton acceptor. Let's put the H plus ion somehow onto that oxalate ion, because then that would cause it to be consumed, and that would shift the equilibrium from left to right as QSP becomes less than KSP. So to come up with a chemical reaction between H plus and C2O42 minus, that's our plan. So there's the oxalate ion. If I add H plus, I'm going to put them together, and then I have a new ion which will have an overall charge of -1. So I'm going to call that hydrogen oxalate, so HC2O4 minus, so -1. And if I did that twice, as in with 2 H plus ions, I would produce a neutral compound. That would actually be called oxalic acid. But either of these reactions would be acceptable, because anything you can do to react with the oxalate ion in some way would decrease the concentration of oxalate, causing QSP to become less than KSP, and again, that would contribute to the increased solubility of silver oxalate in the presence of a strong acid. Now, let's go ahead and look at the official scoring guidelines for the 2022 AP Chemistry exam question 7. They actually gave 4 different possible answers, 2 of which involve the reaction with the hydronium ion, and then 2 of which involve the reaction with H+, as I showed you on that slide. So these 2 that I'm highlighting with that red arrow are what I just talked about. So oxalate reacting with H+ to produce either the hydrogen oxalate ion or oxalic acid. All right, well, that is the official answer to that question. It's also the last question in this packet, so we've come to the end of this video. I hope that you found all of these answers and explanations helpful. Thanks for watching.